Hello, this is Alex Tudor, and I'll be solving the 1996 multiple choice question number 2 for mechanics. A 300 kilogram box rests on a platform attached to a forklift as shown above. Starting from rest at time t equals 0, the box is lowered with a downward acceleration of 1.5 meters per second squared. Question A asks, determine the upward force exerted by the horizontal platform on the box as it is lowered. So for this problem, we're given that the mass is equal to 300 kilograms. The initial velocity is 0, and the acceleration is 1.5 meters per second squared directed down. A free body diagram of this situation would look like here's the box. There's a downward gravitational force and the upward normal force, and this is directed downward from the acceleration, which is downward as given in the problem. So according to Newton's second law, which is acceleration is equal to sum of the forces divided by mass, we have acceleration is equal to mg minus Fn over m. If we plug in what we're given, we have 1.5 meters per second squared, which is the acceleration, is equal to 300 kilograms times 9.8 meters per second squared minus the normal force, all divided by 300 kilograms. If we multiply the entire expression by 300 kilograms, we get 450 equals 2940 minus the normal force. And by subtraction and multiplying by -1, we get normal force is equal to 2490 newtons. And that's the answer for part A. A common mistake that I made was that I forgot that the acceleration was 1.5 meters per second squared, and I assumed that the entire thing was at rest. So what I did was I thought that mg would be equal to the normal force, but I overlooked it and I forgot that the acceleration was given. So just make sure you read the problem before. Part B asks, at time t equals 0, the forklift also begins to move forward with an acceleration of 2 meters per second squared while lowering the box as described above. The box does not slip or tip over. Determine the frictional force on the box. So for this, what we're solving for is the force of friction. And our new free body diagram looks like this. Here's the box. We have a downward gravitational force, our upward normal force, and now we have in the x direction a friction force. So using Newton's second law once again, acceleration is equal to sum of the forces over mass. In the x direction, we have ax equals force of friction divided by mass. And if we plug in what we have, which is we're given that acceleration is equal to 2 meters per second squared in the x direction, we have 2 meters per second squared, equals the force of the friction, which is what we're solving for, divided by 300 kilograms. If you multiply this all out, we have 2 meters per second squared times 300 kilograms is equal to the frictional force. So the force of friction is equal to 600 newtons. The key to this portion is just to recognize that your only horizontal force is friction, and apply Newton's second law to it. Part C asks, given that the box does not slip, determine the minimum possible coefficient of friction between the box and the platform. So in this portion, we're solving for the mu constant, and some equations that we need to know and recognize are that force of friction is equal to the mu constant times the normal force. So we already know from part A that the normal force is equal to 2,490 newtons. So if we plug that into our equation, we have force of friction equals mu times 2,490 newtons. And we also have our force of friction value from part C, which was 600 newtons. So if we substitute that in, we have 600 newtons equals mu times 2490 newtons. And with division, we get mu is equal to 0.24, and that's our answer. And just remember, for mu, there are no units for this. Part D states, determine an equation for the path of the box that expresses y as a function of x and not of t, assuming that at time t equals 0, the box has a horizontal position of x equals 0 and a vertical position y equals 2 meters above the ground with 0 velocity. So given this equation, we have at t equals 0, x is 0, and y is 2 meters. So just to remind you, we have our acceleration in the y direction is equal to negative 1.5 meters per second squared, and it's negative because it's in the downward direction. And to solve this problem, you have to remember that one of the equations of motion are dy equals the velocity in the y direction times the time plus 1/2 times the acceleration times the time squared. So with this, we can say that dy is just y, and we have y equals, and for vyt, velocity is equal to meters per second, and time is equal to seconds. So if we multiply v times the t, that's going to be equal to meters per second times seconds, which cancels out to meters. So let's call vyt, let's simplify that to just y naught. So here we have y equals y naught plus 1/2, and we'll substitute our acceleration in, times negative 1.5 meters per second squared times t squared. So this is what we have this far. Let's simplify that. Y equals y naught plus negative 0.75 meters per second squared t squared. Let's apply this for the horizontal direction. We have our horizontal acceleration is equal to 2 meters per second squared, and the distance in the x direction is equal to the x velocity plus 1/2 times the acceleration in the x direction times the time squared. And we know that the velocity in the x direction is equal to 0, so that cancels out, and we have x equals 1/2 times 2 times t squared. And if we simplify this, we get x equals t squared. And with this, you have to recognize that t squared here can be substituted for the t squared here. So let's bring back our equation. Let's bring that down here. We have y equals y naught plus negative 0.75 times t squared. And if we substitute this in with this equation right here, we have y equals y naught minus 0.75 times x squared. Times x. So the final answer would be y equals y naught minus 0.75x, and y naught is the distance in the y direction. Y naught is the direction in the y direction, and given we have that the y direction, the y original position is 2 meters, so that the dy is 2. So if we plug that into our equation here, we have y equals 2 minus 0.75 times x, and that's our equation. Part E asks us, on the axis below, sketch the path taken by the box. So here I have the graph that was given in the problem, and we know that at t equals 0, y is 2. 2 meters. So we know this point up here. The x-intercept is 2. And our equation from part D was y equals 2 minus 0.75x. So in order to find the x-intercept of this equation, we set y equal to 0. So we have 0 equals 2 minus 0.75x. And with that, we have 0.75x equals 2. And dividing by 0.75, x equals 8/3, which is the same thing as 2 2/3 meters. And on the graph, that's approximately right here. And now we can take our straight edge and connect the dots, or the points. And this is the path that the box takes.